Okay, Organic Chemistry 2341. This is Chapter 8, Part 3. We're going to continue on our addition reactions on different little materials. We've gotten all the way down to the halogenation and hydrohalogenation reactions. Okay, so in halogenation, we have electrophilic addition of halogen across the double bond. Okay, now this typically we want to do this at room temperature in the dark, because if we don't do it at room temperature in the dark, we can have the possibility of having radical reactions happen. When we have radical reactions, that's not electrophilic addition, that does a different chemistry. Okay, so when we do this, we want to put a part of the halide on one side and part of the alide on the other side to give us a vicinal dihalide. So we end up with two halogens on our material. Now, we also want to do this in a solvent like carbon tetrachloride. That does not participate in the reaction, but because it's already halogenated, it does not consume any of the halogen. So whenever we do these reactions, we typically use a halogenated solvent or a solvent that cannot be halogenated, which is why we always do it in something like this carbon tetrachloride, okay? So one of the things that we want to do is that the halogens add across the double bond, because the halogen-halogen bond can be polarized, okay? And so we're taking the electron-rich double bond and helping polarize that bond to make it break apart and give us the addition reaction, okay? Now, the proof we have that the halogen does this is that we have a different mechanism than we have before, and we do not get any carbocation rearrangements, which means we don't go through a carbocation. We only get anti-addition of the halogens across there, okay? So that proves to us that we do not have a carbocation intermediate, but we do have a cation intermediate. So let's look at what the mechanism is on this right here. Okay. So in the halogenation mechanism here, we have the double bond acting as the nucleophile, interacting with half of the halogen. When it does this, it can have the electrons come up from the double bond and then electrons come down from the halogen to create this bridged polonium cation right here. Once we form this cation, we also end up forming the other half of the halogen, takes the electrons with it, and turns into an anion. Okay, so now that we have this cation available to us, and now we have a nucleophile, we can have the nucleophile come in and attack from the opposite side, the bottom of the molecule, because this is taking up the top of the molecule, and we end up with anti-addition. So we have one going on one carbon, one going on the other carbon, and it goes through an anti-addition. Okay, think about it this way. We have the top of the molecule blocked by this halonium cation intermediate, and then the other one has to come at the bottom of the reaction. Okay. So because of this, we have stereochemistry associated with this. Okay. So the halogenation will yield two trans enantiomers, but no cis products. Okay, this has everything to do with the fact that we form that ring on the top of it, and then it has to react with something else. So let's look a little more detail down here, and we're going to use cyclopentene because that we don't have to worry about free rotation, and so we can see where it's happening. Okay, so if we look at this reaction where it's reacting at the top of the cyclopentene, we end up with this three-membered ring forming on the top, which means the halide has to come at the bottom here, and we end up with the trans product here. Notice it's trans product by the fact that the other one, the second one, had to come in from the bottom here. Okay, so what if, okay, fine, let's say that could happen, but let's say the halide comes from the bottom first, okay? So if we look at it from the bottom here, these are actually identical. We can flip those around and make them happen. So, but then once we form that, we have to have addition of the halide to the top of the reaction. top of the chemical. And when we do that, we end up with the other trans isomer. And so these actually are enantiomers of each other. And because you'll have to actually take this one and flip it completely over, and then you'll notice the chlorines would be here and here. So they're enantiomers because they are not fully superimposable, but they are also the trans products because it's an anti-addition. Okay, so let's look at some other stereochemical outcomes when we don't have rings, okay? So let's start out with this symmetrical molecule that's the cis-butene versus the trans-butene here, okay? Remember, there's no free rotation around that double bond, so we can isolate these two different compounds, okay? If we do addition of bromine across this, we're gonna get across the top first and then the bottom second, and we're gonna get a mixture of enantiomers because once we form that intermediate where we have the bromine on the top right here, if it comes at one side, it gets one enantiomer, and it comes at the other side, it gets the other enantiomer. So we have the mixture of enantiomers available to us. Okay. Now, if we were to do that on the trans-butene, we would form that same intermediate where we have the cation above and below the plane here, and when it comes and into either side of this reaction, because of the fact we're starting with the trans, we actually end up with a superimposable system here, and we end up with an achiral meso compound. Okay. So it's easier to see when we use the cyclohexene or the cyclopentene because we don't have that free rotation, but when we do it with these straight chain systems, we actually do see that they create a single achiral meso compound. Okay, so once we form that cyclic polonium cation here, we can actually have it attacked by bromine, or we can have it attacked by other nucleophiles. Okay, when we have it attacked by other nucleophiles, it's going to go anti-addition because, of course, the bromine's being at the top, and when it comes in, it'll ring open to the other side, so we'll get anti-addition. And we will have the nucleophile substituting on the most substituted side just because of the stability of the intermediate. And we can attack it with water or hydroxide or an alkoxide or another halide. And so if we attack it with water or a hydroxide, we end up with a halohyron reaction, meaning we have a halogen and an alcohol on that same product. If we attacked it with an alkoxide, we end up with a haloether. And if we attacked it with a different halide, we'd end up with a bromochloro compound. Okay, so all it matters is that when we form that first bromonium ion, if we had a large amount of a nucleophile sitting around, like in water, we would have attacked by that other nucleophile. Okay, so because of the formation of that bromonium ion, we always get we always get the anti-addition product right here. And so when we get the anti-addition product, we end up with the trans enantiomers. Okay. So let's start with some unsymmetrical alkenes and see where that hydroxide ends up. Now, whenever we form this bromonium cation here at the top, we actually end up with the nucleophile going on the more substituted product, okay? Okay, which means the bromine is going to end up on the least substituted carbon. Okay, so that has a little bit to do with the electronics of it and the fact that the nucleophile comes in and attacks the more substituted carbon, kicking out the electrons from the bromine to give us our product that is this, the more substituted alcohol is formed. Okay, so here's why we think that happens, is that once we form this intermediate right here, is that this side right here is slightly more positive because of the inductive effects, allowing the nucleophile to come in and attack this section instead of attacking at the other section. Okay, so let's say we wanted we wanted to add two hydroxides across the system and we want to do it in a syn fashion. Well, we have a reagent that can do that. This is called osmium tetroxide. And the reason it works is that we actually are going to take the osmium tetroxide material itself, and we're going to add two oxygens across the same side of the double bond to give us our intermediate here, this osmium complex. And then by reducing off this osmium complex to cleave the metal bond, we end up with two alcohols on the exact same side. Okay. Now, the fact is that once it does that, it generates the osmium dioxide right here. And so you either have to use a stoichiometric amount of osmium tetroxide, or alternatively, you can use a co-oxidant in the system. You use just a little bit of the osmium tetroxide, but then you use something that's going to oxidize the osmium dioxide back to the tetroxide. And what we can use for that is what we call N-methyl morpholine and oxide. And so this heterocycle here is called morpholine. And by having this oxygen here, actually it's a radical anion. And so we can transfer this oxygen back to the osmium to regenerate osmium tetroxide. And therefore we can use a catalytic amount of toxic osmium in the reaction, and therefore we can make this a very safe and easy operation to give us a cis diol. Okay, so let's go over all the different types of addition stereochemistries we have so far. Okay, so in halogenation, we end up with a 50-50 mixture of syn and anti. Okay, because of that hydrohalogenation, we end up going through that carbocation intermediate. In acid catalyzed hydration, we again go through a carbocation intermediate and we have a mixture of syn and anti. When we go through oxymercurization, the mercury sticks to the system, so it doesn't allow the rearrangement of the carbocation, but it does allow for a mixture of syn and anti addition. And if we used an alcohol instead of water, it does the same thing. Now, in some reactions, we only get syn addition. In the hydroboration, to form that primary alcohol, we have syn addition. In catalytic hydrogenation, we have syn addition because it adds across the same side of the double bond. And in syn dihydroxylation, because the osmium tetroxide hits on the same side of the double bond. Okay. Now, in reactions where you only get anti are the halogenation reactions, because we form that bromonium cation intermediate where it's sitting on top of the double bond, and then with the halohydrin or any other nucleophile that comes in attack, we only get anti addition. Okay, so by choosing our reagents, we can get a mixture of syn and anti, we can get syn only, or we can get anti only.